Hey folks, how's it going? This is Mr. Murray coming to you with a do now for Course 1 Honors for Friday, May 8th, 2020. Welcome to the end of another week. Wow, it really does go by so quickly. So, in this do now, we're going to continue the theme of building up our skills with just graphing them. And all I want to focus on is just plugging in numbers, seeing what comes out, and looking what the graph looks like, right? Let's just like a different kind of thing, because I think the ability, right, to test these points and see what comes out is just such an important skill, no matter what kind of function you're looking at, and it's something that always will give you a sense of what the function looks like. So let's take a minute, think about some important values. I'm going to give you, so yesterday, if you look back at yesterday's do now, I filled in the table for you. I'm going to give you a couple of numbers. We should probably plug in 0, 1, and 2. Okay, but we also need to have negatives. So I also want to see -1, -2. And then you need to choose a third number of each for your own. It could be like a number and its opposite. That's totally fine, but you need to add another number of your choice. All right. So please take a second, pause the video, fill in the table, create a graph from the table, and then when you're ready, unpause, and I'll show you what I got. Okay. So remember, whenever you do, well, first of all, remember that this is an exponential function. Okay? And it's called an exponential function because x is in the exponent, right? So that's a way to remember that. So when I do anything to the power of 0, I get 1. And when I multiply 1 by 3 halves, I get 3 halves. All right, now when I do 2 to the power of 1, I'm going to get 2. 2 times 3 halves. The 2's will cancel out, and I will get 3. You can actually think of this almost like a geometric sequence if you think about it. Watch. Because now when I plug in 2, I get 2 squared, right? I'm thinking about plugging in 2. 2 squared is 2 times 2, which is 4. Now, if I do 4 times 3 halves, the 4 will cancel, become a 2, right? So I'll get 2 times 3, which is 6. So you can see it's multiplying by 2. 3 halves times 2 is 3. 3 times 2 is 6, right? Because this is like an explicit rule for a geometric sequence. If I do 3, I'm going to multiply by 2 again, 12. Okay, what about -1? So if I do 2 to the -1, it's going to become 3 halves. So I'll write -1 here so we know what I'm doing. So 2 to the -1 is 1 over 2. So we've got 3 quarters. And lastly, -2, right? I got the 3 halves, and then 1 over. So if I do 2 to the -2, that's 1 over 2 squared. 2 squared is 4. So 2 to the -2, right? That's 1 over 4, and that would be 3/8. So basically, you can think of negative powers like this. Instead of multiplying by 2, you're dividing by 2, right? Because think about it. When you go down by 1, 2 to 1, you divide by 2, 6 to 3. When you go down 1, 1 to 0, you divide by 2, 3 to 3 halves, right? 3 over 2 means literally 3 divided by 2. When you go from 0 to -1, you divide by 2, right? You go from 3 halves to 3 quarters. So that's another way to think about it, is just like we thought about arithmetic sequence. And this is why with arithmetic sequences, I was getting you to think about the idea of adding one way and subtracting the other way, because we have a similar thing here, right? Multiplying one way, dividing the other way. Okay, so let's go ahead and make a graph here. So we have 0, 3 halves, and 3 halves is basically 1.5. Maybe you're starting to see some pattern with the role that 3 halves plays in the graph. We have 1, 3. We have 2, 6. And we could try to squeak on 3, 12 if we wanted to. Then I have negative 1, 3/4. Negative 2, 3/8. That's a little bit less than a half. And it will do something like this. Okay. So again, this is an interesting kind of growth, right? So as the function goes from left to right, what's happening, right, is that the outputs are essentially doubling, right? As I go down the line, as x goes up by 1, y is doubled, essentially, right? If you think about it like that, what that means, like I said in previous videos, is the greater the current output is, the more it's going to grow for the next output, right? So for example, when I'm at 1 and I go to 2, I go up by 3. But now when I'm at 2, I go up by 6, right? So having more to start with means I'm going to grow by more as I go from step to step. And that's the unique type of growth, right? Remember with linear was it's always going up by 1, right? Or it's always going up by 4, whatever the slope was, or down, right? Right, with a quadratic, it was, we talked about like this rule with like 1, 3, 5, or like 2, 6, 10, or something like that, depending on what A was. We talked about that. And with stuff like, I don't know, absolute value, again, it depended on A, there was some kind of fixed or like patterned amount that we could figure out, right? And it was a predictable pattern. Here, it's not as easy because it depends. The output depends on the previous output, right? How much you grow depends on how much you have. So hopefully you're able to get this right. If so, amazing job. In a moment, what I'm going to do is I'm going to go down to a bonus example. I encourage you to take a look at that because it's going to look at another thing that sometimes happens when we graph exponential functions. Otherwise, have a wonderful weekend, and I'm looking forward to another great week. Okay, so now down to our bonus example. So notice this one, I'm kind of trying to have you think about what happens as you mess with the number in front of the 2 to the x, right? So now I'm going to make that number negative. And remember, when you're plugging in, we have this notion of PEMDAS here, right? PEMDAS, no matter what, always tells you the order that you're going to evaluate. And so what this means is that when we plug into the exponent, right, the only thing that stops this from having a value is the x, right? Once you plug a number in and you say this is x, this expression is going to have a value. However, what's being done here is, because of the lack of parentheses, you're raising 2 to the power, and then this negative is coming at the end. So this is essentially negative 1 times 2 to the x. And if you look at it like that, you can see that if we're doing PEMDAS, we have to do the exponent before the multiplication. So I'm going to choose some numbers. Let's choose some good ones to explore. So 0, 1, 2, 3, 4. Remember, the thing with this is that the growth happens so quickly that you're going to quickly be off the page. And I'm only asking you to graph what you can see, right? I'm not going to ask you to find a number that's way off there. All right, and then I want to see, let's try -1 and -2. So let's try to see if we can do this together. So anything to the power of 0 is what? It is 1. Okay, so we'd have 2 to the 0, which is 1. So it would be -1 times 1. And that is -1. So we have 0, -1. Whoa! Below the x-axis. That's interesting. So I don't know if we've seen this before, but now we have a function that got below the x-axis, right? Usually we had, right, this barrier. It would get close to 0, couldn't touch 0, but it would get closer and closer and closer. But it would always stay above. Now somehow it's gotten below. Let's see what, this is weird. Let's see what happens. So we plug in 1. So we have our -1 times 2 to the power of 1. And 2 to the power of 1, remember, anything to the power of 1 is itself, and that is -2. So 1, -2. Interesting. Looks like a line, right? But we hopefully know better that it is not a line. So now I've got -1, and now I've got to do 2 squared. And 2 squared is 4, and that's -4. So the issue is that if you're doing -2 to the x, this is not the right thing. And you can see why. So if you do -2 off the bat, if you plug in 0, you're going to get 1, and 0 is not 1, it's -1. So off the bat, even plugging in 0 doesn't work. 1 might work, okay. 2, you're already going to get another disagreement. So you got to really, as with the quadratics, right? I really pushed being careful with that. So you got to really be careful with those signs. So now I'm going to plug in 3. So I've got -1 times 2 cubed, which is 8. So it's -8. So I've got 2, -4, 3, -8. So it looks like this is making it go the other way. Now, if you think about it, what's different about this function? Well, let's see in a minute. Now, this one, but maybe be thinking about that. We'll get -16. Now, -1, if we do 2 to the -1, we get a half. So this is -1/2. For once, it's actually technically a larger value because it's less negative. And this would be 2 to the -2 is 1/4 because it's 1/2 to the 2. And that's -1/4. So we have something like this is what you're going to end up having. Because for the same reason, if you continue to make, essentially what's going to happen is you're going to just do, well, it's still going to come down to the fact that you're doing 1/4, an 1/8, a 16th, a 32nd, a 64th, a 1/28th. It's never going to become 0 because the number in the top is always going to be 1. And so you have this similar idea, but the fact that we now have a negative means that this is no longer always increasing. This is always decreasing, because if you go from left to right, you're always going down. The numbers, the y values, are always getting smaller. They're getting more negative. Okay? You also have a function that has a little bit different of a range, and you're going to have to think about that, because now there's going to be a negative infinity in your range instead of a positive infinity in your range. So lots of things to think about here. Okay, so as we move forward into this exponentials, it's going to be extremely important to think about how you graph. Please, please, please hold on to the strategy of making a table. And as we go from function to function, just find a strategy for making the table that's quick and painless. I know we don't necessarily want to make the table. I know we a lot of times think it's a lot of work. So then find a way to not make it so much work and then you can get a table that will make you a perfect graph every time. All right, best of luck, folks. Don't forget to love math, and remember, you can do it. Until next time, have a wonderful day.